אני מניח, הנושא של הקורס הוא, לא זוכר מה השם שלו, אבל פיזיקה, מתמטיקה פיזיקס. ואגב, יש פה מישהו שדרוש לו ששפת הקורס תהיה אנגלית? כן? אוקיי. So let's switch to English. To the best of my knowledge, this is the routine here that in this course, if anybody needs a course in English, we will switch to English. So in any case, this is a mathematical physics course. Not many administrative announcements, so it's the course is a course. At the end there is an exam. I think that the exam determines 85% of the grade, while the rest is for homeworks. What else should I say? And of course, I've forgotten to bring the book, but clearly the textbook is Bender and Orzag, something that asymptotic method for something and something. The holy yellow book. Everybody should have it at home. Okay. Any questions about that? Yes.
About the exam at the end, it's for some reason in the second semester.
It's been updated since then.
Okay.
Okay.
But yeah, I also noticed.
By the way, feel free to ask questions in Hebrew and I will translate or whatever. So first few words about the mathematical physics and why it is so important. So first of all, you can look at, please transfer it between you. This is a gravestone of somebody, real gravestone. And on the gravestone, it said that this guy took to his grave the secret of how to solve the equation fourth root, right? So 2 plus x to the power of 1/4 minus, I guess, 2 minus x to the power of 1/4 equals 1. Right? So this is the main achievement of this guy in life, I'm afraid. And but unfortunately, it's a solvable problem. So you can on this page, I wrote also the answer, which is x equal to the 1/2 square root, I guess, of minus 73 plus 28 square root of 10 or something like that. So this is a solvable equation, okay? And now the point is that if you don't want if you want your gravestone to look better, you better be expert, have better knowledge in mathematical physics. Okay, so what's important is that this is something that I always say at the beginning of this course and the other course that I'm teaching, that first degree in physics, so what you have gotten in during the last 3 years is to some extent a fraud, right? And the reason is that when teaching students, we always solve solvable problems, and the homework are also made of solvable problems. However, the generic problem is not solvable, right? If you write a differential equation, just write a second order differential equation. It is not a solvable equation. and even equations like Bessel equation, right, is not solvable. People have generated tables of the solutions, and now we call it Bessel functions, and we know that because we are familiar with it. Because, it's not by and large things are not solvable. And the main problems when you enter the realm of research is that you start confronting real questions, real problems, and these problems are not solvable. Generic integral is not have no function, you cannot integrate. Generic differential equation you cannot solve. So what physicists are doing is trying to map everything to harmonic oscillator, or free particle, or to completeless square, or Gaussian integral, and so on and so forth. But there is some limitation to all these tricks. And at the end of the day, one have to confront hard questions. And what should we do in this case? So there are exactly two methods. Method number one is to use numerical analysis with all its problems, but this is one method that one can try to adopt in order to deal with problems that we cannot solve. And the other method is what we are going to do in this course. Right? So this course is focused on the one and only method by which one can approach problems that are not solvable. Okay? And what is this method? The general name is perturbation theory. Right? So when I ended up my first degree in physics, I got the impression that perturbation theory is a branch of quantum mechanics. No. Physics is a branch of perturbation theory, for reasons that I will explain in a minute. Okay. So what is perturbation theory? We start with hard problem, right? And we want to solve the hard problem. In order to solve the hard problem, we will identify a small parameter in the hard problem that we will call epsilon. And then we will try to such that when epsilon is 0, I can solve the problem. And then I will try to write this full solution of the hard problem by a power series of the form sum from n equals 0 to infinity, say, of an epsilon to the power of n. So a0 will be the solution of the hard problem when epsilon goes to 0, and when the hard problem when epsilon goes to 0 should be easy problem, right? And then we expand it in a power series. In a minute I will give an example, right? I understand that it sounds abstract, but in a minute I will give an example, right? So this is and this is the mechanistic, now you can turn the knob, right? You can you know a0, and then you can determine a1, and then you can determine a2, and then you can determine a3 until you figure out the whole power series, right? Up to a infinity. Okay. Now, what do I want to say? Right? So this is an infinite walk, but okay, let's assume that we did that. What we have to do now, after we wrote that, we have to substitute epsilon is 1 and to sum the series. And this will give us the answer. Right? This is the trick. First of all, write it as an infinite power series. 2, calculate all the elements of the power series. 3, substitute epsilon equals 1 and sum the series. This is the prescription. Of course, there are many problems with this prescription. but because this is very abstract, let's start with an example. Not important, but just to see an example. Okay, so here is my example. I have the horrible equation x to the fifth plus x equals 1. This is at least a quintic equation, and you know that the equation that I wrote before, the one from the gravestone, was first order equation, and these equations are solvable. But quintic equations, by and large, are not solvable. Okay, so how do we solve such an equation? Suppose that we need urgently, we desperately need a solution. How do we solve this equation? So first of all, just in order to have some basic idea, I will a baseline. I will write the numerical solution of this equation. X equals 0.75488. Right? Of course, you can continue. Right? This is a numerical solution of this equation. By the way, how many solutions such an equation have?
5.
5, because of the fundamental theorem of algebra. And this is the only real solution, I think. Okay. So how do we start dealing with such an equation in order to get number that will be close to that? Okay. Now I'm going to demonstrate the simplest, the fundamental approach of perturbation theory. I'm taking this equation and I should add an epsilon. So I put here epsilon. Right? Good. Now, can I solve this equation when epsilon is 0?
Yes.
Yes. What are the solutions?
1.
1. Okay, I'm just focusing on the real solution.
-1.
Right?
Right.
If epsilon is 0,
Oh, yeah, I thought it was
1 to the power of 5 is 1.
Okay.
So when epsilon goes to 0, this is hard problem, but when epsilon is 0, it's an easy problem. Okay, good. So we start with x naught, I will call it, equals 1. Now, let's try to calculate the first correction. Okay? If epsilon is 0, then x is 1, but we know it is not 1. This is x. Okay? What is the first order correction? So let's write, now I would like to write x as x0 plus epsilon x1. As x0 plus a times epsilon. A1 times epsilon. I will call it A0. A0 is 1. And I will write x as A0 plus A1 times epsilon. These are the first two terms in this infinite series. Are you with me? Right? Or maybe I will write it in general. X is A0 plus A1 times epsilon plus A2 times epsilon squared plus A3 times epsilon cubed plus blah blah blah. This is exactly that. Okay? And now what I can say about that, I can say that if epsilon goes to 0, then all these terms are 0 except for the first one. So I know immediately that A0 is 1. Right? So I will, okay, A0. So A0 is 1. Now, let's do the next step. What is the next step? As I'm saying that now x, I assume, is 1 plus A1 times epsilon. And my goal is to calculate A1. So I plug this into this equation. What is 1 plus A? And I'm calculating everything to first order in epsilon. every higher power of epsilon, epsilon squared, epsilon cubed, I will neglect. Only first order in epsilon. Okay? So what is written here now is 1 plus epsilon A1 to the power of 5 plus epsilon times 1 plus epsilon A1 equals 1. You see, I plugged this here. All the rest of this sum is higher powers in epsilon. So I don't need them. Are you with me? Okay. Now, again, I want to calculate only the first order in epsilon. So what should I do here? Which terms I have to save? I have 1. What is 1 plus epsilon A1 to the power of 5?
1 plus epsilon A1. 5 epsilon A1.
5. 1 plus 5 epsilon A1 plus terms that are higher order. Okay? Plus epsilon, which is epsilon times 1. And do I need this term? No, because it's epsilon squared. All this is equal to 1. Okay? You see, this is the first order in epsilon calculation. Now, of course, the way I build it is this one and this one cancels out. And it turns out that A1 is, of course, the epsilon cancels out. And it turns out that A1 is 1 minus 1/5. Okay? So, the way I can write now x as, okay, I can write, so, maybe I will erase this. Yes. So I can write x as 1 plus A1, plus minus 1 minus 1/5 of epsilon plus things that are higher order in epsilon. This is the, right? And if now I will plug epsilon equals 1, because what I'm interested in is not this equation, but the equation x to the 5th plus x equals 1. So the epsilon equals 1. What I will get? 1 minus 1/5, we see, which is 0.8. And this is not bad. This is 0.75, right? Okay, so let's continue. Okay, how do we continue? So in order to continue, I would like to remind you that, where should I write it? Let's write it here. 1 plus delta. Delta is a small number. I'm just using it instead of epsilon because I'm using epsilon here. To the power of 5 is 1 plus 5 delta plus 10 delta squared plus 10 delta cubed plus 5 delta to the 4 plus delta to the 5. Just it's not, what's the technical name? Multinomial, I think. Okay? If it's the power of 2, it's a binomial, but what?
I think binomial means there are two arguments.
Yeah,
Multinomial is
binomial
only
means
half
two
x
arguments,
equals
so that would still be binomial.
Still binomial. Okay,
two
binomial.
arguments.
Okay,
Yeah,
fine.
that
So-
spells triangle.
But in any case, okay, but it's not fair because delta is actually all that.
Yeah, but the expansion is still
Okay,
binomial
fine.
expansion. Though.
Okay, this is the binomial expansion. Fine. Okay? So we are going to implement that, and let's do the work up to third order in epsilon. Okay? We did first order, now third order. So what I should do, I'm using, so now I have this equation, right? And delta, my delta is actually A1 epsilon plus A2 epsilon squared plus A3 epsilon cubed. I don't need any other thing because I want everything to set third order in epsilon. Okay? And now I expand it and I keep only third order in epsilon. Okay? So the x to the 5, right? The x to the 5 will be what? Will be 1 plus 5 A1 epsilon plus 5 A2 epsilon squared plus 5 A3 epsilon cubed. You see, this is the first. This was the first, the zeroth term. This is the first term in the binomial expansion. And now I need the second term, so I need all this squared, but I'm keeping only terms that are up to epsilon cubed. Yes?
What happened to doing it to the second order? What?
Now it comes. Here it comes.
But you're doing to the third.
No, this was that.
Okay.
Now I'm going to that.
Okay. Okay.
Yes? Now I have plus
10 A1
10 A1 squared epsilon squared,
plus
and I have plus 20 A1 A2 epsilon cubed. You see? And I don't need anything else because this is already epsilon cubed. And for the third one, okay, so I collected all the terms up to epsilon cubed that are here and here, and now I need this one. From this one, what I will get?
10 A1 epsilon to the third.
Only this. So plus 10 A1 cubed epsilon cubed. Okay? And all the other terms are of order which is higher than epsilon cubed. Good. Now, what about x or epsilon x? Okay? So epsilon x will be what? Will be x is 1 plus blah blah blah. So epsilon x will be epsilon plus epsilon squared A1 plus epsilon cubed A2, end of game. Okay? And I want this plus that to be 1. Yes?
Is there any particular reason we did the delta thing? Or
What?
did we have to do this delta equals, or can we just use epsilon and remove it?
No, I just wanted to remind you how the binomial expansion looks like, and I use delta instead of epsilon because delta is both small and not epsilon.
That makes sense. But yeah.
Okay, so now we want to calculate the answer, and I'm going to do that order by order in epsilon. So to the order epsilon to the 0, what I have is 1 equals 1. Right? I have this 1, right?
Supposed to be A2.
This plus that should be equal to 1.
In the second equation, it needs to be A2. No?
A2, not LB.
A2, sure, of course. Thank you very much. Okay, so first equation, to the power of epsilon to the 0, all I have is this one and this one. And of course I build it in, it should be easy problem for epsilon to the power of 0. Now what I have for epsilon to the power of 1?
minus.
This is what we actually did. We have this term and this term. And from this term and this term, we find out that A5A1 plus 1 is 0, so that A1 is 1 minus 1/5. Right? And this is what I wrote here. 1 minus 1/5 epsilon, and if I put epsilon equals 1, I will get 0.8. Okay? Next. What's happened to the power of epsilon 2? Okay. Now I should take into account who? This guy, this one, and
10A1 squared.
anybody else?
Yes, 10A1 squared.
This one.
Yes.
Okay. So I have 5A2. Of course, the epsilon squared is a common denominator. I can filter it out. 5A2 plus 10a1 squared. But a1 I already defined. This is the trick. Every step allows you to calculate the next step. So a1 squared is 1 over 25. So I have here plus 10 over 25. This is that. And I have also that, which is what? Which is a1, which is minus 1/5. But 1/5 is 5 over 25. And therefore, I realize that a2 is what?
Minus 1 over 25.
I have here 5 over 25, and I have 5 here, so minus 1 over 25. Right, so I've calculated now the next term here. Minus 1/5 epsilon minus 1 over 25 epsilon squared. Right? So what is my estimation? Right? For when epsilon goes to 1, I will have that. Now, how much is that?
0.76.
0.76. Right? So you have 1, you have 0.8, 0.76. Even closer to our goal.
This gives us the real part. What about the imaginary?
Wait. No, I mean, I'm thinking now about the real solution. Okay, now what about epsilon cubed? Who are the participants? So we have, in epsilon cubed, we have 5a3 what else we have? 20a1a2, but how much is 20a1a2? This is plus 20 over 125, because a1a2 is 125, okay, and I should multiply it by 20. Now we have 10a1 cubed. a1 cubed is minus 1 over 125, and I should multiply it by 10, so minus 10 over 125. And we have also a2, plus a2, which is minus 5 over 125, because a2 is 1 over 25 minus, okay? So what's the conclusion?
Minus 1 over 1.
How much is a3?
Minus 1 over 125.
I have 20 minus 15, so it's 5 over 125. It cancels with this 5, so I have minus 1 over 125. Good. So I can write it now, the minus 1 over 125 epsilon cubed. And again, if I will put epsilon equals 1, I will get here 1 over 125. And this takes me to, I had from the first 3, I had 0.76.
I will guess 0.755.
I'm not sure, but you can check. Did I wrote it here? 0.752, according to what is written in my notes. You are welcome to check. Okay? So, and so on and so forth. Right? Now, here is the question. Can you guess the next term?
Minus 1 over 725.
Plus.
Hmm?
So the plus.
What will be the next term?
1 over 625.
Okay. So 1 over 5 to the 4. No, it's 0. So a good physicist will stop here and say, well, I know the answer. But in this case, the good physicist has to consult a bad mathematician that will tell him that it is wrong. Okay, the next term is 0, just to show you that it's not always reasonable to extrapolate. Okay. Now.
שאלה.
Yes.
זה במקרה שזה נראה כמו סדרה, כאילו? זה יכול גם...
It should be a series. This is by construction. by construction, we are expanding everything in a perturbative series, assuming that epsilon is small parameter. Okay. But suppose, so now, suppose that, but you see that calculating the A1, A2, A3 is just a mechanistic work. You have to turn the knob, every turn of the knob, it spits another A. Okay, and you can do that. Suppose now that we have an exact formula and we know what is the answer. What is the answer for all A's. Okay? What will be our final mission? Right? Our final mission is we have X as a sum from n equals 0 to infinity of an epsilon to the power of n. And now we should put epsilon equals 1 and sum the series. Okay? Or maybe we want it, we want a 1/2 here. No problem, put 1/2. Maybe we want 2. Okay? Point to put 2. Okay? You see the point? Now, here comes a very delicate issue that will govern a substantial part of our activity. Well, not a mechanistic trick. A substantial part of the activity in this course. The issue is, can we sum this series? So we plug epsilon equals 1, say, so we have to sum this. What's the problem?
Why it doesn't go to 0?
A must go to 0. In the it's
tail
going to
of the
infinity.
series must be
The series must be convergent series. Right? If the series do not converge, then all what we are doing is garbage. Okay? You see the point? Our ability to do something depends on the convergence properties of the series. Now, by the way, something that I've forgotten to say. What allows me to ask every power separately to be 0? You see, I said all the coefficient of epsilon to the 0 must be 0. All the coefficient of epsilon 1 to the power of 1 must be 0. For every term, all the coefficient of this term must be 0. Why I can do that? Why it cannot happen that the epsilon squared term cancels somehow the epsilon terms?
Because near the when epsilon is 0, you're estimating the function f of x equals 0. All of its derivatives are 0 too. So you can't.
To some extent, okay. In other words, maybe, I mean, you have a good intuition, but in other words, Taylor series is unique. Right? There are no Taylor series with different coefficients that converge to the same number. Right? And this means that I can calculate it for every epsilon by itself. Good.
If we are good physicists and say after the third term we don't need the rest, why do we need the series to be converged?
Because if the series is diverging, it implies that when you stop at the second term, you neglected infinite contribution, which is prohibited even for physicists. Okay? Okay. So here is the main question. And now, do you expect, so you see, just intuitively in this series, you see that the terms, the ANs are becoming smaller and smaller, but you have the epsilon. And if epsilon is larger than 1, say, if epsilon equals 2, then the epsilon terms are becoming larger and larger. So the question whether or not this series converges is questions about the asymptotic behavior when I'm taking A to A infinity, an for n large. What is the ratio between an when n large and epsilon to the power of n when epsilon is larger than 1, right? So actually people have analyzed this problem, and it turns out that the
Wait, what is this?
point 1.649, this is epsilon, right? The series will converge until this point. So I have to remind you that Taylor series have a radius of convergence. The closest point, if this is now actually the complex plane, so this is real epsilon, and this is the imaginary part of epsilon, and there is a circle here of radius 1.649. Once you have a Taylor series that converges, it will converge until it will reach the radius that corresponds to the first point in which it does not converge. Right? So in all this region, this series will converge. Maybe we cannot calculate all the terms, but if we will be able to fulfill the mission and calculate all the terms and do everything, then the species will converge and our program will work. You see, if I'm taking epsilon equals 2, then our series is not going to converge, which means that the first three terms will give me no indication for the actual sum of the series, because the sum is infinite. Yes?
I'm still a bit confused about the significance of that a over epsilon to the n and the significance of this. We are looking to find an approximation, like a series approximation for our x, for,
yes,
for this, the thing that makes the equation 0. Why do we need this series to converge? Why do we need the... Why does... it's just a bit fuzzy.
Suppose I will try to find the solution for the equation x to the fifth plus 2x equals 1. Right? Epsilon equals 2. Right? In this case, this series, even if we calculate all the terms, is not going to converge.
Okay. I thought the point was always to make epsilon equal 1, to define the changed equation in a way that works.
No, I mean, suppose that I have this equation.
Okay.
I'm trying to plan a car or, I don't know,
So what if you do
a spaceship, and I ended up with this equation.
So what if you do 2 epsilon x? What if you do 2 epsilon x? Then epsilon goes to 1.
No, if you do 2, I mean...
Okay, yeah, that doesn't... Okay.
Okay, you see what I'm saying, right? If the series is not converging, then apparently all this program is meaningless.
And yet you will have a root. Right?
Ah, very good. So you pointed out a very important point. But very important thing. The fact that the series do not converge does not mean that this equation have no root. Clearly it has. Right? Clearly it has. But apparently, when we will try to calculate it using this power series, we will get garbage. Okay? Because we are starting for small epsilon, so we are expanding here, and this expansion ended up here. If you want a very simple example, take the function 1 over 1 plus x. Right? This function have a top power series sum over n of, okay, 1 plus epsilon, say, right? Sum over n of, okay, what is the power series? You remember?
Epsilon.
It's 1 minus epsilon plus epsilon squared minus epsilon cubed and so on and so forth. Okay? So it's a sum of minus 1 to the power of n, epsilon to the power of n, from n equals 0 to infinity. That's the power series of this function. Right? Now, what's happened when epsilon is 1?
Zero.
This power series will not converge. right? Because if you leave 1, minus 1, plus 1, minus 1, plus 1, minus 1, this is not a convergent series. So you have no answer, right? And if epsilon is larger than 1, then actually you have things that are going up and down, but the amplitude is growing. Okay? Now, what's the reason for that? The reason for that is that if I'm asking what is the radius of convergence of the Taylor series, I should look for the closest singular point. What is the closest singular point? In the epsilon, in the complex epsilon plane, right? If this is real epsilon and this is image epsilon, the closest singular point is epsilon equals minus 1. And this determines the radius of convergence, which is 1. So when I'm taking the power series to be larger than 1, I will get something that do not converge. Nevertheless, the function exists. If I'm taking epsilon equals 2, this is 1/3. The function exists, the answer exists, but our power series will not give us the right answer. You see what I'm saying? So apparently, according to what I have presented you until now, if I will try to use perturbative expansion in order to get some idea about the root of the answer for physical problem, then I should be able to convince myself that the power series converges. Otherwise, there is no meaning to the power series. Now, here comes the most kept secret, most kept black secret of physics. None of the power series, of the important power series in physics, is convergent. None of them. All the interesting problems for which we use perturbative expansion are cases where the power series does not converge. Right? Now, if you were you have taken course of quantum physics, right? What example of power series of perturbative expansions that show you?
Spin.
Half WKB approximation.
No, WKB is the technique. For what physical problem power series was implemented? Perturbative expansion. For?
Close angle approximation.
The dimension time oscillator.
And you have a harmonic oscillator?
Harmonic oscillator is solvable.
No, but like you.
Usually they give you either harmonic oscillator with constant field, right?
Yeah.
Or Zeeman effect.
We have not.
Hydrogen atom with magnetic field.
We have not done that yet.
What?
We haven't done that yet. We're doing quantum 2 now.
You have to sue your teacher.
Quantum?
Zeeman effect must be taught as an example for perturbative expansion. What?
Started quantum mechanics 2 now. So,
Okay, whatever.
yeah.
So, the point is that these guys are lying to you. Both Zeeman effect and harmonic oscillator with a constant field are solvable problems. You don't need perturbation theory. They are solvable, completely solvable. Right? And that's why the perturbative expansion converges. But for problems that are not solvable, the perturbative expansion do not converge. Right? Never. Never, I mean, not, yes, never converge. For reasons that I will explain to you in a minute. Yes?
Can you give an example of a problem that where perturbative theory is important? That you do
Yes,
use it?
sure. You want to calculate, okay? Are you familiar with this equation?
Yes.
What is that?
Quantum
Quantum harmonic oscillator. What is the ground state?
Gaussian bell curve.
Yes, and what is the ground state energy?
H bar omega half.
Yes, 1/2 h bar omega. Great. Quantum harmonic oscillator, solvable, Hermite polynomial, bala bala, bili bili. Now, add here something like, I don't know, B, let's call it, just to have a coefficient that will take care of the units, x to the 4. Right? Okay, this will be epsilon. Sure. This is a quartic oscillator. Okay? And there is no solution for that. Okay, you can say that the solutions, you can define the solution as a solutions of the quartic oscillator, but I mean, there is no, there is no solution for this in terms of elementary functions. So the only thing you can do, if you want to know what is E naught, right, you can write E naught of epsilon is equal to h bar omega over 2, which is E naught when epsilon goes to 0, plus a power series in epsilon. Very good. But this power series is not convergent. Right? And none of the important power series in physics, there is not a one that converges. Quantum electrodynamics, it always happens that the power series do not converge. Now, you have to understand that this is a question about, it's an existential question about what is our license to do physics, right? Because when the first, I mean, when in the old Greek world, right? They have mathematics, they have physics. They didn't implement mathematics to physics. Right? Why? Because they were smart. And they said, mathematics has to do with perfect objects. With, if you have a disk, it's a, I mean, all the points that are inside the perfect circle. If you have a, I don't know, a square, it's a square, right? An ellipse is an ellipse. Now, in life, there are no perfect objects. The tire of your car is not a disk, right? It has all these blah blah things, I mean, that are there. So we cannot implement mathematics. Mathematics is for perfect objects, for, you know, heavenly things, for the stars, yes. They want to, they had classical mechanics, because they wanted to understand the stars, because they believe that the stars are doing from ether, which is a perfect thing, right? But they didn't implement it also to music, which is also perfect. But they didn't implement it to real life problems, because they think mathematics is not adequate for describing real life things that are not, because you have to deal with objects that are not perfect. The first guy who started implementing mathematics in order to describe worldly things like pendulums and so on was apparently Galileo. Right? And when Galileo started to do that, people asked him the same question, right? How can you implement it to a pendulum? When you write the equation for the pendulum, you assume that this is, you know, a point mass on a rigid rope, but this is not the case. There are so many little things that make a difference between, you know, what people are doing. That the physicists are always solving for, you know, spherical cow in polar coordinates, but the cow is not spherical. So what is your license to do physics, to implement mathematics to nature? Now, Galileo didn't have an answer. He simply claimed that what he's doing works nicely, so he didn't care. But if there is an answer, what's the answer? The answer is perturbative expansion. That I can take the differences between the perfect pendulum and the real pendulum. There are differences, but they are not big. They will affect the motion, but they will affect it only slightly. So I will solve something, I will have an epsilon, which is the difference between the perfect objects, the mathematics of a pendulum, and the actual thing that I'm kicking back and forth in my lab. and I will find out somehow that this is not a big correction. But apparently when you actually do the perturbative expansion, you find out that the perturbation theory do not converge. So apparently the whole program of Galileo was wrong in the first place, but thanks God he didn't have a good mathematician to consult with. Right? Maybe Euler was able to understand the problem. Okay. So just in order to continue with this example and to show you an example in which the things do not converge, right? So, I mean, quartic oscillator is also an example, but let me try to, okay. So, let's go back to the original question. Now, you remember we started with this and we said, hey, this is an equation we don't know how to solve. We should put an epsilon. Right? We should put an epsilon such that we will be able to solve the problem when epsilon is 0. And I decided to put the epsilon here. This was my decision. Can you suggest another option? Put the epsilon here, right? Put the epsilon here, and perfect, right?
That wouldn't work.
What?
You can't diminish the most dominant.
I can do whatever. I'm
But if
finished.
x is less than 1, then it becomes the most.
I do whatever I like,
thing.
right? I want to put the epsilon here,
If x is less than 1, that becomes the
and then if epsilon is 0, I have x equals 1, and I will expand it in a perturbation theory. And what's nice here is that I can do it all that now without any effort, or almost with no effort. All I need to do is what? I started with that, so now all I have to do is to put the epsilon here, right? So now here this will be epsilon, and here I should add another. So this is epsilon squared. This is epsilon cubed. I don't need this term anymore because this will be epsilon to the power 4. This will be cubed, and I don't need these two. Goodbye. Now here I don't have the epsilon, so this will be 1, this will be epsilon, and this will be epsilon squared.
You
That's
need
it.
to add the coefficient.
Hmm?
The coefficient of the 5.
You need to add epsilon to the
Yeah, epsilon to the third d.
Sure. And I have to add epsilon cubed A3. Good. And I have to erase all the garbage that they put here later. Okay. So let's work. What are the coefficients of epsilon to the 0?
epsilon.
No, epsilon. What coefficient are not going to 0 when I take epsilon to 0?
1.
Right? Only this one and this one. Okay? So to the power of epsilon to the 0, I have 1 equals 1, which is correct, and this is because I must take it when epsilon goes to 0, it must convert. It must be an easy problem. So now what's happened when epsilon wait. I will also use this. Right? I will use this. Okay. Now what's happened when I'm taking epsilon to the power of 1? Yes. epsilon to the power of 1, I am taking these two terms. So it tells me that what is A1? A1 plus 1, A1 plus 1 is 0, which implies that A1 is minus 1. So I'm putting here minus epsilon, and if epsilon is 1, I have minus 1. So you remember last time in the first step we get from 1 to 0.8, so it becomes closer. Now in the first step we get from 1 to 0. Okay? Now, okay, what about epsilon squared? Who are the coefficient of epsilon squared?
5A1
I have 5A1
and A2.
and A2, right? So 5A1 plus A2 is 0, okay? But A1 is minus 1, so A2 is plus 5, right? So I have here plus 5 epsilon squared, and if epsilon is 1, I have here plus 5. So you see we started at 1, we go to 0, and then we jump to 4, when our goal is 0.75, blah, blah, blah. Okay? Next. What about epsilon cubed? I have 5A2 plus 10A1 squared plus A3, right, equals 0. So what is A3? 5A2 is 25. 10A1 squared is 10. And A3, what is going on here?
Minus 35.
Minus 35. Okay? So I have here minus 35A cubed, epsilon cubed, sorry. And here I have minus 35. Okay? So the series gives me, right, 1, 0, 4, minus 31. Very bad. You see what is going on here. I mean, this is a very bad power series. Okay, it goes up and down, and the mismatch between this and the correct answer is only growing. Okay? Good. So, the question is, actually, okay, but suppose epsilon was really small. So this is when I would like to put epsilon is 1, right? What will happen, but there is still a chance that this will converge nicely if epsilon is very small. Like if epsilon is 1 of 1,000, right? So I have a very tiny, and this is 5 over million, and this is 35 over a billion, so it goes down, right? So one can ask, what is the radius of convergence of this series in the real epsilon, image epsilon plane? And it turns out that that I didn't write it. 0.08192. So it converges in a very tiny region around 0. So I forgotten to tell you an even worse part of the secret, that I told you that most of the power series in physics do not converge. Not only they do not converge, the radius of convergence is 0. So even if the parameter you are expanding it in is as tiny as you want, still it does not converge. So this is like, this horrible thing is even better, is still infinitely better than the power series we're using in physics. Yes?
Isn't it, when you have a radius of convergence at 0, you have some sort of התבדרות בנקודה הזאת? Like exploding behavior?
Okay, I will elaborate on that later on.
Okay.
Yes?
When using this, how do you determine the order of A, of epsilon to dissolve?
Sorry?
They picked a third order for epsilon, but why didn't it go to fifth order?
Okay, that's, I mean, you have to separate the discussion between the practical part and the theoretical part, right? So theoretically, in order to justify the whole method, you have to calculate higher orders. I completely agree that every normal physicist who is not Russian or French will calculate the first order, will give the PhD student to calculate the second order, and will never calculate the third order. So Kondo actually got the Nobel Prize for calculating third order correction for something, right? He was the first one that has the courage to calculate the third order. But the principle is important, and actually for you, I will ask you later on to calculate the corrections for the ground state of the anharmonic oscillator to 80 orders in perturbation theory, but I will show you how to do it quite easily. Okay. Good. Now, as you have already pointed out, the problem why this is so much worse than putting the epsilon here is because when I put the epsilon here, I'm changing the highest order of the equation, right? And this, because this the equation, when epsilon goes to 0, I have an equation that have only one root. And when epsilon is finite, I have 5 roots. Right? So I'm doing something horrible to the equation, I'm changing the structure. And this is always the case, that when the small parameter is in front of the highest derivative or the highest power, we are in a big problem. But this is also the generic case, because for example, in Schrödinger equation, the small parameter h bar is in front of the second derivative, right? Good. So, so I will not in this lecture. I'm not going to show you. I mean, the whole course will wander around all these problems, and we are going to learn a very strong a series of very strong techniques to deal with these problems. And the interesting thing is that there is a black magic that one can use, and with this black magic, the horrible power series like that are much easier to. It is much easier to extract the correct solution from the horrible power series than from the normal power series. But okay, this is just הבטחה לעתיד. And now let's continue with our beloved equation, the quintic equation, and I would like to use it in order to demonstrate or to give an example of some part of the important techniques that we are going to use again and again and again in this course. So, first of all, I would like to introduce you with two mathematical symbols. Now, these symbols are used all the time by people, but not accurately. So, in this course, they will have a very accurate meaning. First of all, the first symbol is So first of all, what we are going to start to introduce now is asymptotic analysis. And the first statement is that f of x is asymptotic to g of x as x goes to infinity, or to something, to x naught. X naught, to something. In our case, epsilon goes to 0 or whatever you like. Right? So I want to speak about this. What's the meaning of this wiggle? People are using it, I mean, is approximately like, but I want to define very accurately what's the meaning of that. The meaning of that is that the limit when x goes to x naught of f of x divided by g of x is 1. Right? Do you understand that? Okay, questions. Is sine x asymptotic to x as x goes to 0?
Sin x over x goes to 1.
Huh?
Sin x over x goes to 1.
Sine x over x when x goes to 0 is 1. Good.
Looking at the Taylor series expansion. Also just looking at the Taylor series expansion.
Yes. So is e to the x asymptotic to 1 as x goes to 0?
No. Yeah.
Yes. E to the x over 1 at x goes to 0 is 1. Okay? Is x cubed asymptotic to 0 at x goes to 0?
No.
No. Very good. How do you see that? Put it here.
Because, yeah.
Nothing is asymptotic to 0. Right? Is x cubed asymptotic to x cubed plus x to the 4 as x goes to 0?
Yes.
Yes. You see? But what's happened when x goes to infinity?
They are.
No. Okay? Do you understand what asymptotic to means?
Can you repeat?
If you write x cubed divided by x cubed plus x to the 4th, and you take x, yeah, right? You take x to 0, then the x to the 4th is negligible with respect to x to the cube, so you have 1. But if you take x to infinity, this is going to 0, because it goes like 1 over x, right? Okay. So this is the first thing that we are going to use, asymptotic to. Yes?
Wait, so this causes some like unintuitive things to happen. Like you have x squared is asymptotic to x squared minus 1.
Right?
When you go to
Right.
infinity.
The differences, note that x cubed is asymptotic to x cubed plus x squared at x goes to infinity.
So the difference.
But the difference between them is going like x squared, so it can be 10 gazillions,
Yes.
right? It's only the ratio between them that is going to 1.
You're saying relative to the value, the difference is small.
Yes, yes. So,
Okay.
so for example, are you familiar with the counting of prime numbers, right? Okay. People were asking how many. If you start, you have in the first 10 numbers, you have 2, 3, 5, 7 are prime, right? Okay. But of course, the higher and higher the number, it's more difficult for big number to be a prime number. Why?
There are more
Because it may be divided by many smaller numbers, right? So the question was, how the number of prime numbers is growing with n. Right? Put a cap at million. How many prime numbers you have up to million? Billion. How many prime numbers? So Gauss have suggested that that the number of prime numbers up to n is equal to the integral between 1 and n of 1 over ln n. Right? And this goes like more or less like n over ln n. Am I right? I think so. Ln n over n. Something like that. I think it's n over ln n. It's called the logarithmic function of Gauss or something like that. Okay? So, I mean, Gauss suggested it by calculating, I mean, sitting with a
it's n
pencil
it's
and
x over log x. You're right, n over log
okay.
n.
So Gauss did that by calculating all the prime numbers up to billion or something with a pencil and a piece of paper and extrapolating. Right? This was his. And then the question was, can one prove it? Okay? So actually what's happened is that people have succeeded in proving that pi of n is asymptotic to the whatchamacallit of Gauss, the suggestion of Gauss, meaning that as n goes to infinity, the right number of primes divided by that is going to 1. But this does not, this gives no bound on the difference between these quantities, right? Because maybe if the difference, I mean, if this is going like n over ln n, right? Then if you have something that is going like n over ln squared n or ln n, it will still be asymptotic. Okay? You see what I'm saying? Now, people do believe that the difference between this and that as n goes to infinity is smaller than, I think, square root of n ln n or something. Right? Something like that. But to show that is equivalent to prove the Riemann hypothesis. So if you want to get the Nobel Prize for mathematics,
And $1 million.
what?
And $1 million.
And $1 million, and you know, and to be the most famous mathematician in the last 100 years, you are invited to show that. But so this is just in order to give you the idea of what's between being asymptotic to and being equal. Okay. So this is the first concept I would like to put forward. The second concept is the idea of f of x is negligible with respect to g of x as x goes to x naught. Again, it's very important that without this comment, these relationships are meaningless. Their only meaning is at a limit. So the question is, what does that mean? That means that as x goes to x naught, f of x divided by g of x is going to 0. These are the basic relationships in asymptotic analysis. Asymptotic to and negligible with respect to. Both of them are at a given limit, right? So again, a few examples. Can I say that x squared is negligible to with respect to x as x goes to 0?
Yes.
Yes. You see? Can I say that minus x squared is negligible with respect to 1 as x goes to 0?
Yes. No.
Yes. Yes. Even though, what do I want to say? I want to say it the other way. What do I want to say? Or maybe I would like to say something like that. X squared is negligible with respect to minus 1 as x goes to 0. Okay? So x squared is larger than minus 1. You see, but it does not contradict that it is negligible with respect to minus 1 as x goes to 0. Right? So this negligible with respect to is not much smaller. Don't make the mistake. This is not much smaller than. Much smaller is, by the way, in any case, is not well defined. I mean, is 3 much smaller than 35? I don't know, right? So, but this is a very rigorous definition, and much smaller means exactly that, and not, and it can be larger in absolute value. In absolute value, I don't care. Okay. Having introduced these two ideas, these two basic tools of asymptotic analysis, now I would like to analyze the equation epsilon x to the fifth plus x equals 1, this one. Now I really want to know what's happened when epsilon is actually small. So it's not in the context of expanding everything and putting epsilon equals to 1. I want to know what is the solution when epsilon is small. What is my problem? My problem is that, as I said, when epsilon is 0, I have only one root. When epsilon is finite, I have 5 roots. So what's happened to these to the other 4 roots? As I'm taking epsilon to 0, what's happened to the 4 roots?
They are negligible.
They eat each other.
I mean, if you're taking...
I'm taking epsilon to be 0.1. I have 5 roots. I'm taking epsilon to be 0.01. I have 5 roots. 0.001. I have 5 roots. 1 in a million. I have 5 roots. 0. I have only 1 root. Where the other 4 have gone?
They become closer to each other.
What? Okay. So now we want to analyze that using the tools of asymptotic analysis. So my trick is that. Right? I want to analyze this as epsilon goes to 0. Okay, I replace the equal sign by asymptotic 2 sign at epsilon goes to 0. Now, and here comes a very, very important, I know that you are a little bit exhausted, but still try to hold on, because here comes a very important aspect of asymptotic analysis. What I'm going to do now is called dominant balance. What is dominant balance? Okay. I would say when epsilon goes to 0, I have 3 I have three elements. But I expect when epsilon goes to 0, only two of them are big, and the other one is small. Why? Why I expect that? Just because, I mean, I hope, generically this is what will happen. Right? Generically, when epsilon goes to 0, I will have two big and one small term. And the question is, what are the possibilities? Okay? So how many possibilities I have? Three. So I may assume that as epsilon goes to 0, epsilon x to the 5 is equal to 1 and x is negligible. I may assume that x is equal to 1 and epsilon x to the 5 is negligible. And I may assume that epsilon x to the 5th is plus x equals 0, or epsilon x to the 5th. Okay, I should replace this by asymptotic 2. Okay. Is asymptotic to minus x, and 1 is negligible. See? These are the three options. Okay? How do I know what to choose? I have to check for consistency. So, for example, if epsilon x to the 5 is asymptotic to 1, this requires that x is asymptotic to epsilon to the power of what? To the power of 1 minus 1/5. You see? You agree with me? Now, if x is going like epsilon to the power of 1/5, as epsilon goes to 0, it implies that what x is doing when epsilon goes to 0, it goes to infinity, right? Like epsilon to the 1/5, right? So x is not negligible with respect to 1. You see? This is 1 when epsilon goes to 0. This is 1, and x by itself is going like epsilon to the minus 1/5. So this suggestion is inconsistent. So I don't like it.
It's negligible relative to what? Because you could have that sure.
I started with 3 terms.
Yes.
I decide to keep these 2, assuming that this is negligible as epsilon goes to 0.
And you get it as
And now I got that when epsilon goes to 0, this term is much larger than all the others.
Okay,
This is not a self-consistent choice.
You could have that this term would go to infinity, but slower than all the others.
Yes, that will be consistent. Okay. But now it goes to infinity when the other 2 are order 1.
Okay.
Okay. Now, what about this suggestion? Is this suggestion consistent? Yes. Yes. You see? If x is asymptotic to 1 as epsilon goes to 0, then epsilon x to the 5th is going like epsilon and is negligible with respect to x and to 1. Right? So this is a consistent choice that gives me x equals 1. What about this choice? If epsilon x to the 5 is going like x, forget about the minus. The minus is not important. This is orders of magnitude, right? If epsilon x to the 5 is going like x, it implies that epsilon x to the 4 is going like 1, right? So x should go like epsilon to the power of minus 1/4. Okay? And if x goes like epsilon to minus 1/4, this one and this one is going both like epsilon to the 1/4, because minus 1/4, because they balance each other, dominant balance. But this one is actually negligible. You see?
Is negligible.
So this is also a consistent choice. So you see what we did. We have actually found the asymptotic behavior of the 4 solutions. One of the solutions is x equals 1. The other 4 are going like epsilon to the minus 1/4.
Why do you know one of them is doing that and 4 of them are doing that?
What?
Why do you know the numbers of which, how many are doing which? Why do you know one of them is this and 4 of them are that?
Because this is 4th order equation. That's the 4 solutions. So I can write epsilon x to the 4 equals to, so it's epsilon x to the 5th equal to minus x. So epsilon to x to the 4 is equal to minus 1. So x is going to like epsilon to the minus 1/4 times minus 1 to the power of to the power of 1/4. Now, how much is minus 1 to the power of 1/4? It's e to the I omega, say, where omega is 2 pi over 4. So, I mean, if you look at it, it's here. This is the real x and this is the image x. The real epsilon and image epsilon. X. And as epsilon goes to 0, these 4 roots,
2 pi over 8.
I mean, these 4 roots are going to infinity. So this is where they are going. They are going to infinity. Okay? So this is how, what's happened to the missing roots when epsilon goes to 0, they escape to infinity. Okay? And last thing, if now I want to know, okay, I know that when epsilon goes to 0, they go to infinity, but how I will get any idea of what they are doing for epsilon finite, I can also generate perturbative expansion for these roots. How do I do that? I should look, instead of x, I see that x is going to infinity like epsilon to the minus 1/4. So I will define y as x times epsilon to the quarter. Which implies that as epsilon goes to 0, x goes like something like epsilon to the 1/4, meaning that y is order 1. Okay? So y is order 1 as epsilon goes to 0, and then I can write x as y divided by epsilon to the 1/4. Now let's write this equation for y. What is this equation for y? I have epsilon times 1 to the 5th divided by epsilon to the 5/4. You see? Plus y divided by epsilon to the 1/4 equals 1. In other words, epsilon divided by epsilon to the 5/4 is 1 over epsilon to the 1/4. And now I multiply everything by epsilon to the 1/4. I'm getting y to the 5th plus y equals epsilon to the 1/4. So this is great. I can write perturbative expansion for small epsilon in y, because y will not diverge when epsilon goes to 0, right? Y have no problem. It kept order 1, and this allows me, so I know that y to the 5th plus y is 0. I mean, so now I can write perturbative expansion the same way. The only difference, remember before I always told you that I have sum of a n epsilon to the n. Here it will be sum of a n epsilon to the n over 4. It will be a fractional power of epsilon in the expansion, and this is important because, I mean, this happens in many cases, that we end up with fractional powers of epsilon. Now, okay, the rest is for the homeworks. Yes?
Will you see the same things if you switch the epsilon? like the normal way, like x to the power 5 epsilon x goes like 1.
Here?
Yeah, but change the epsilon.
No, but this one is not diverging with epsilon goes to 0.
That's fine. I just want the first thing we do in the class, like change the epsilon. Like
Yes.
Will you see the same thing?
If I will do the perturbative like x to the 5 plus epsilon x equals 1?
Yeah.
No. Because now I do not have any roots that disappear to infinity as epsilon goes to 0.
Mhm.
Right? Because when the dangerous, this is called in physics, right? Such perturbative expansion is called weak coupling. Right? You have yes. And this is strong coupling, because the small parameter is a coefficient of the highest order, either in the derivative or in the power. And this is also involves some sort of a singular perturbation theory in the senses that I will explain later in this course. Okay, so all this story is sort of an introduction that where I used very not important equation in order to demonstrate the basic ideas of how this that will appear again and again and again in this course. And in the next lecture next week, we will start to deal with differential equations, because this is what physicists are doing, right? No, not solving. Usually, we do not encounter how do you call it? The name of these equations after some Greek guy. Call him? מה? איך קראו ליווני הזה שכתב את הספר על המשוואות האלה?
איזה משוואות?
כל המשוואות מהסוג הזה. לא, נו. מה? ברח לי השם שלו. מעצבן. מה?
מאיפה הוא? יווני. יווני.
קופץ לי כל הזמן עכשיו בראש ארקימדס, אבל זה לא ארקימדס, אלא... מה? לא.
אוקליד היה גיאומטריה.
על המצבה שלו יש חידה שאומרת שחמישית מהחיים שלו הוא היה צעיר, ואז... דיופנטוס.
אבל זה לא משוואות האלה, זה משוואות עם אינטג'רס.
נכון, לא משנה, אז...
זה משהו...
טעיתי, בסדר, אוקיי. סליחה. פיין, אז בדרך כלל אנחנו לא פותרים משוואות כאלה, אבל יכול להיות, לא משנה, אבל משוואות דיפרנציאליות זה מה שאנחנו עושים לפרנסתנו, אז עם זה נתחיל שבוע הבא. אוקיי.
I'm your teacher assistant of the course of Math for Physicists. My name is Dmitry Weitzer. And today we will discuss with you differential equations, ordinary differential equations. I don't think that today we will cover something that you don't know. We will mostly discuss basic ODEs course in a one and a half hour, and from the next lesson we will discuss local analysis, and the rest of the course will discuss global analysis and perturbation techniques. So let's start. What do you remember about ODs? What is it? How we solve them?
Equations that involve the function's derivatives.
Mm-hmm. Okay.
how to solve them. There are a bunch of techniques, but mostly like separation of variables or yeah, basically.
So yeah, we can write ODE in this way. In most general way. Right. And we can split ODE to two big classes. The first one is linear differential equations, and the second one is nonlinear. And the linearity defined by this right-hand side. So if f is a linear function of x, y and its derivative, so we call this equation linear. If it has some dependencies like square root or some power of y prime, etc. So we call it nonlinear differential equations. And the most well-known linear differential equation is this one. How do we call this equation? Yeah.
Ordered. So like if it was x equals 2, it would be second order, third order.
Yeah, but in general, this is nth order differential equation with constant coefficients. This a1, a2, and etc. till an. It's just some constants, some numbers. And what is the general solution of
Infinite series. Infinite series. A series.
Series?
No, it's exponent.
Yeah, right. General solution is y equals to e rx. And if we plug this solution to the equation, we will get a polynomial equation, right? So we convert our differential equation to just algebraic equation. And we know that if it's nth power equation, it has to have how many roots? N roots. Yeah. So then we got n roots, and the general solution will look like some constant c1 e to the r1x plus c2 e to the r2x plus etc. plus c n e r. So these constants called constants of integration, and in order to find them, we need to have n initial conditions, right? So, but what happens if some of the roots similar, the same? For example, we have three exactly the same roots.
You get x.
Hmm?
You get x.
X. Okay.
To the solution. X times the exponent.
So if we, but it's only the case then we have two.
The number of times.
You will
Okay.
need the less boundary conditions.
No, but boundary condition is something different.
Initial.
There are initial conditions and boundary condition, but it's a different question.
The exponent times the first coefficient plus the C2 times x plus C3 times x squared.
Yeah, till the, so if you have m similar, m same values of r, we just have like C1 e to the r x, then C2 x x, so on, C2 m minus 1. Yeah. This is for repeated roots. Okay. You also can write this equation in a much simpler form using the differential operator.
Ring function.
Hmm?
Ring function.
Yeah, it's related to it, but I need something else. So it's A1. Basically, this is the same equation. Also, if we have nth order differential equation, we can rewrite it as a system of n first order differential equations. Do you know how to do it? For example, in physics, where can you see this, the same technique?
Can you repeat again the question?
I said that we can rewrite this equation, this is nth order differential equation, to the system of n differential equations, but they will be first order with the first derivative.
Pendulum.
Say it again.
Pendulum.
Coupled.
Okay, but the question was more general. So you have Newtonian law, second Newtonian law, right, with the second derivative. But how you can formulate physical problems, but with the system of two first order equations?
We let the first derivative, it's a t or something like that, and
Okay.
we get a two differential equation from order 1. It's like to have y tag is t and t tag is y.
Basically, I meant
Like that?
Hamiltonian and Lagrangian mechanics. Yeah. For example, in the Hamiltonian equations, or Lagrangian equations, you have a system of n differential equations. They are not system, but in the Hamiltonian it's two differential equations, all of them first order. But basically, they describe the same system in the same principle as Newtonian mechanics do. So. Yeah, basically, to rewrite these equations, for example, we have y double prime plus 3y prime plus y prime. Let's let's rewrite these second order differential equations into system of two first order equations. How we can do it? You try to set the
Let's put the first derivative is t.
is t. Okay,
It's some different parameter.
like this.
And let's get the derivative of t is the second order derivative of y,
Okay.
and we can substitute this in the equation.
But what is y?
So integral it's t squared.
Yeah, but how to do it without integrals? Again, you have to get a system of equation, not just one equation. Should be two equations.
What is the question?
How to rewrite these second order differential equations into a system of two differential equations of first order? This is the question.
Let's put in the same way. Let's define two parameters. It's t1 and t2.
Okay.
And define the y is t, and the derivative of y is.
You can
T1 is
Y.
okay.
The derivative of y. T2 is the derivative of y. Let's get the derivative of these two equations.
Okay.
T1 prime
Right.
Yeah, it's
This is the first one. Okay.
Yeah.
And the second one?
T2 prime is the second derivative of y.
No, we can use this one.
Yes.
Right? Like
yeah, yeah.
3 t1
T2.
prime. Yeah, t2. Thanks. Minus 5t1. Right? So we transfer our second whole differential equation into a system of two first order. Yeah. Sometimes it's much easier to solve systems of system of differential equations rather than original one. So, but obviously you can go not only this way but vice versa. Have a system of 5 first order differential equations. You can rewrite it as a one equation of fifth order. So basically the same. Okay. Couple words about initial value and boundary value problem. Maybe someone knows what's the difference between initial value and boundary value problems. No?
No.
Like
the initial.
mathematically?
Yeah. How do they usually define the initial value problem and the boundary value problem? What's the difference? I mean, can I have for a particular differential equation initial value problem and boundary value problem, or this is only for a particular set of differential equations? I can ask about initial value problem for one set and for another set just about boundary value problem.
Wait, you're asking if for certain differential equations you could have initial conditions, for others you could have boundary?
Yeah, just in general, or it doesn't matter to what equation.
Yeah.
second one.
Oh, it's meta.
For example, for this equation, can I solve this equation and use initial value problem? Why not?
There is a multiplication between the different parameters.
Who thinks differently?
You need the initial conditions.
In principle, I can write general solution as we discussed.
Yeah, but you
Here.
have a
Right?
coefficient. You need the initial condition to find the coefficient.
Right. And the question is, what's the difference between initial values, initial value problem, and boundary value?
The boundary give you the right solution for the system. It's like
And the initial
not give you the coefficient of the solutions.
Okay.
Initially, it's a point on the surface, and boundary it's the surface itself.
It's a set of points.
Yeah.
Right. So, for example, I have some general solution here, right? Actually, we can solve this system, this equation. Doesn't matter. So, for example, how many conditions should I have here? Two, right? Because it's second level. For example, this type of initial condition is called initial value problem because it's in one point in the function and all of its derivatives, right? But if I write it like this, so this would be the other problem, which is called boundary. Yeah. In principle, we can solve this and this. By the way, do you know how to solve this equation?
There.
You do a Taylor series expansion.
Just a Ricochet equation. Yeah. So you find solution in the form x to the r. Okay. Okay, for example, let's imagine that we found n solutions of our equation. How we can say, is it linear independent set of solutions or not? What can we use? Because otherwise, if the set of all solutions linear dependent, it couldn't be the right solution for the equation. Do you remember about Wronskian? No?
Yeah, but I don't think Fourier will also Fourier will not give the right.
Fourier?
Yeah. Because they must be orthogonal.
But how you gonna use Fourier?
Yeah, that's the problem.
So let's imagine that you have n order differential equation. In this case, we not constant coefficients. And then somehow you found a set of functions. So y1 of x, y2 of x, the equation of nth order has n different solutions. And they have to be linear independent. So if we want to understand whether this solution is linear independent or not, we need to calculate Vronsky. Basically, it's determinant of this matrix. And if for all x's it's not 0, then we can say that this is the proper set of solutions.
What do you call the W?
It's Vronsky.
Can you write it? Vronsky?
Vronsky.
Why not determinant?
Say it again?
It's the determinant של ה...
Yeah, it's a determinant.
Yeah.
Yeah.
Okay. I don't hear the...
Vronsky, it's not a matrix. It's not a matrix. It's a determinant. Yeah.
I'm having flashbacks to first year physics.
It was a very long time ago, right?
Yeah, that was when we learned. So it's like really
30 years ago.
honestly.
Wow. You have no chance to remember it.
Yeah. Okay.
Okay, let's solve some problems. Yeah, one thing more. I forgot to tell you about inhomogeneous differential equations. So now what we discussed is homogeneous differential equations with right hand side equals 0. But sometimes you have problems with non-zero right hand side, and you need to know how to solve these types of problems. Someone remember how to
You solve for the 0 and then you expand for the overall.
The solution is sum of two solutions, the homogon one and the general one.
Yeah, but in the general case, you have n solutions, so you need to sum all of them. Basically, yeah, for example, here there is some function of x, right? And in the first step, we solve homogeneous differential equations, then right-hand side equals 0, then we find this set of n functions, right? And then we can use method which called variation of parameters. So how we that's how we find our solution, particular solution for the inhomogeneous equation. So our particular solution is some function u1. Then I write it for the second order differential equation. Okay. So in this case, we have two solutions. Y1 and Y2 we know from the homogeneous. So it's a solution. They are solutions of homogeneous differential equation. Then we need to define these two functions. Now they are known, but we can define them actually using this Wronskian. So we calculate Wronskian of these two functions, y1, y2, y1 prime, y2 prime. So y1, y2 prime minus y1 prime, y2. This is our Wronskian, and then for x equals to minus integral y2x f of x divided by Wronskian, and u2 is the same integral but with y1 of x f of x divided by Wronskian. And then we calculated all of these integrals. We just plug these functions to this equation, and then the general solution of inhomogeneous differential equation will be sum of all these n functions plus the particular solution of inhomogeneous problem. In case of two second order differential equations will be two functions, y1 plus y2, and plus this particular solution. So it's basically how we can solve inhomogeneous equations. Okay, let's try to solve one homogeneous equation. The equation is y double prime minus 3 over x, y prime minus plus 4 x squared y ln x. First step, we're solving homogeneous equation, right? Then run right hand side equals 0. In what form we
multiply by x squared, so you get resolution.
Okay. Then solution x to the r. Then we need to plug the solution to the equation. We'll have x r plus 2 minus 3x r plus 1 plus 4x to the r. No.
The derivative.
Yeah.
So
Should
r
be
squared
like this, right?
with the r squared and 3r.
Like
Because
coefficients.
Yeah, like this.
when you
Yeah. Sorry about that. Yeah. Now good. Okay, then we see that we can rewrite this like r minus 1 minus 3r plus 4 0. It's not 0 because it's our solution, right? And this should be equal 0. Right? Have r squared minus 4r plus 4 is 0. One and 4.
Minus 2.
1. Just 2. Not minus 2. Yeah, we have double root. Okay, then two solutions for homogeneous problem is
x r of 2 and x of 3.
Let's see one.
yes some constant, right? Like a x squared. Here is b x squared and
Times x.
Plus x.
No, wait.
Plus x plus cx.
no.
Kb.
No. When we solve Euler-Cauchy equation,
Plus
in,
one.
in the case of repeated roots, we have to multiply by logarithm and its powers. So in case of double root, we just multiply by ln x. If it will be three roots, then the third solution will be ln squared. So that the logic is the same as for the constant coefficients. Okay. We found this solution. What was the next step? The next step was to calculate the Wronskian. Right? So Wronskian x squared ln x. I don't need these constants for calculating those. Then derivative of this to x, right? And here's derivative of multiplication, so it's 2x ln x plus x.
Wouldn't it be easier to use Sturm theorem?
I don't think so. I don't think so.
Okay.
At least you need to know what is Sturm-Liouville theorem. So, yeah. Okay. Then we have 2x cubed ln x plus x cubed minus 2x cubed ln x. So this and this go away. Have x cubed. So it's not 0, except of 1 point, right? But that's okay. If you have only 1 point, their Wronskian equals 0. That's fine. Still your solution is linear independent. Okay. The next step is calculate these two functions.
to, in our case, this one. So x square ln x multiplied by right hand side. In our case, it's 1x. And we need to divide it by Wronskian, so by x cubed. Okay, we have ln square x divided by x, the x with minus, don't forget it. How we can calculate this?
Ln cubed of x. Not like the cube of the natural log. Times a constant.
Yeah, like we have dq is the x over x, which is d ln x. Right? Then we have integral q q squared dq, right? So this is q cube over 3 with minus, so it's minus ln cube x divided by 3. Okay. This is our first function, and the second one we need to plug in y1, yeah, x squared, right hand side 1x divided by Wronskian x cubed, then ln x over x dx. The same integral, right? And then we got ln square x over 2. Yeah. Good. Then the final solution will be for so the particular solution is u1 is minus ln cube x divided by 3 multiplied by y1 x squared plus 1 squared x by 2 multiplied by, so it's also 1 cubed x squared. Actually, we can add these terms up. So it will be x cubed and
Divided by 6.
yeah,
I know.
here's ln x. This is our particular solution, and the general solution for the problem is ax squared plus bx squared ln x plus squared 6 ln cubed x. Yeah. That's it.
You don't have to add a constant and we do all that.
No, when we calculate particular solution, we take all the we take solutions of homogeneous equations without any coefficient. So yeah, just as it is, without a and b, and
as you know, if we solve in second-order differential equations, in the answer we should have only two constants. And no need to write any constants here in the particular solution. Okay. By the way, sometimes we actually don't need to solve the differential equation to find Wronskian. There is a beautiful formula called Abel's formula, and using this formula we actually can calculate Wronskian up to constant. So, in general case, and for the differential equation with non-constant coefficients, so we can easily calculate Wronskian by solving this equation. W prime equals to minus p and minus 1 of x. What is the solution of this equation? Yeah. So the Wronskian, just some constant a, e to the power minus integral p n minus 1 of x, the x. So no need to solve. And if you know the value of Wronskian, you can easily say that some equation that you're going to solve, is it solvable or not? Is it do you have unique solution, or you don't have solutions at all, or maybe infinitely many solutions? So let us see the examples. So we know that general solution of this equation can be written in the form of y of x, the sum of ci y I of x I from 1 to n. Okay. And then, for example, we have initial value problem. That we have to have conditions and n conditions, and for example, y for the initial value problem, for all of the functions that are represent solution, we have the same point, right? In this point, we have some value of the function. So this set of initial points we can write as I not like this. So in every point have different in point x naught have different values of these functions. Yeah, it should be this. This is derivative. So we have like for j equal 0, we have just y x naught plus y naught. Then for j equals 1, we have y1 prime x naught is a1, and the half of set of equations. So it's n equations. And from linear algebra, what do we know about when this system of equation has a unique solution?
W not equal to.
What is it, W? No, from linear algebra.
Yes, the determinant not equal to 0. All
Okay.
the 8. All the A's are not linear dependent.
Yeah. And if we look on this, we can exactly say that the only condition then this system of equation has unique solution is then actually Wronskian is non-zero. Because if you write this system, you will see that these functions yi, they create, and our goal is to find these coefficients, right? So basically, we understand that uniqueness of the solution is this condition. And then we can use this and this to say something about differential equations. Is it solvable, or is it has infinitely many solutions, or you can't solve it at all? So let's see. For example, this problem. So we're gonna solve this equation. No, not solve, just try to understand whether it's solvable or not. And we have two initial conditions. Y of 1 equals 1, and y prime of 1 equals 2. And using this we need to understand something about this equation. So actually we don't need to solve it. We can just calculate Wronskian, and if it's 0, then we can say that this problem is not solvable with this initial condition. Wronskian will be e to the some constant first, e to the minus integral, and here is p n minus 1. So we need to look at this coefficient, right? 1 plus x divided by x. Okay. So we can split this integral into 2, right? The first one is just on x, right? And the second one just x. It's our Wronskian. And now we see in our initial conditions. So if we plug in x equals 0, equals 1, is it okay or not?
It's gone off early.
Yeah, but it's not 0, right?
Yeah.
Then this point of initial condition is well, and this equation is well defined. So we hope that this equation has a unique solution. But for example, if I took a different initial condition, for example, in x equals 0, in this case, what we will have here?
0.
No,
No.
Infinity, right? Yeah. Because ln of 0 is minus infinity, yeah, and exponent to the power of infinity is infinity. And then the problem is not defined. So you can use it as a shortcut to define whether a problem is well defined or not well defined. But again, if Wronskian is not 0, it doesn't guarantee that problem you can solve the problem. So it's like a necessary condition, but not sufficient. Okay.
So if Wronskian is 0, it's not
0 or infinity. Yeah, you on this step can say that something with initial conditions here wrong, and you cannot actually get one unique solution. But if it's non-zero, still you need to begin to solve it. Otherwise, you don't know. Okay. What else? Let's try to solve a different equation. ideas? Just first order equation. Is it linear or not? No? Yeah, because here's y in power minus 1, right? It's not linear. Okay? But still it's first order. Maybe we can find some new variable to substitute.
Maybe define z
It's
equals
multiplied.
1 by 1 over y.
Z equals this one. Okay, let's try. Then we need to, so y is 1 over z, right? And the y prime is minus prime z. Right? And then you have minus z prime over z squared. The left hand side, right hand side, 1 z x plus
Turn it down to linear.
It's better. Multiply by z.
Z squared, right? Then we have minus z prime to z over x plus z. Okay.
And we have to substitute.
Keep. Yeah. Seems to doesn't work.
Let's multiply the differential equation by exponent of the power of integral of 1 over x.
And
That.
then, what will be the next step after you multiply?
We have derivative of multiplication of two functions.
Maybe z should have been y divided by x. And then
no.
derive it with respect to x.
We should get the new variable and rewrite the equation in terms of new variable. So here we have y, unknown function. Maybe
tangent have
tangent. Okay. Tangent y or
well,
No, lan. You.
do you remember something about Bernoulli's equation? From the course
Bernoulli?
of Bernoulli, yeah.
z should be y to the power of 1 minus to the power of 2. Like it's y minus 1.
Y minus is in the power of what?
2.
Like this? You want to try this?
Let's multiply the equation by y.
By y? Okay.
Yeah.
Okay.
The differential equation.
Okay. And then?
Y tag. Let's define another parameter. Let's call t is y squared.
Okay.
Take the derivative.
Then t over 2, t prime over 2
is equal to
t over x plus 1.
That's weird.
Yeah, it's easy. It's a linear equation. How are we going to solve it?
Pick it out to one side, and then you basically have regular OD.
Shift the
Solve homogeneous. First, remove the 1 and solve for the exponent, and then just add a constant to the end of the exponent. Plug it in with adding a constant at the end.
So, rewrite it in this way.
Yeah.
Okay. But it's not a constant coefficient, right?
Maybe integrated
But
factor?
you have, yeah, integrated factor.
Yeah, but no, you can do it in. It's x plus a constant. I can already see that.
Multiplied by x.
Okay.
All the equation.
Well,
Yeah, so now plug in x to the r first with 1 equals 0.
No, it's supposed
Ignore
to
the
be
1.
equal
Okay.
x, not
Okay.
It's supposed to be equal.
no, it's supposed.
So it becomes.
You do t prime is dt of dx.
It's supposed to be equal
Well, to
x,
separate
not equal zero.
variables, right?
Equal 1.
Okay.
maybe just shift the origin.
It's a second. The solution should be a second order polynomial.
Just separation
Yes,
of variables
separation.
without any polynomials. So dt over
Wait, it's supposed to be x there, it's not plus 1.
No.
Because you multiplied by
It's
x.
yeah.
So now you
Right,
do have
yeah,
to
yeah,
do
yeah,
that.
yeah. It's not.
Maybe,
I have
maybe
a-
just shift the origin by -1. Like define I don't know, q equals t minus 1, and then q prime equals t prime.
Yeah,
Yes,
but now we
yes,
don't
so-
have 1.
Yeah, but you
After
can still
multiplication,
solve the
right?
homogeneous part, and then for the
You
particular
can
you
guess
You can.
like t equal ax squared plus bx plus c.
Again?
Ax squared plus bx plus c.
What? Do you notice something strange in this solution?
Without the C.
Too many.
You can,
yeah. Okay, but still the equation is first order. You have two constants.
It's not. It shouldn't be x. It should be ax squared plus b.
Why we wouldn't
You
solve
didn't
it
say
like
X.
before?
No, I think it's in the x it's
It
fine.
shouldn't be. It should be ax squared plus a constant. Not
Okay, but still it's strange that you have two constants in the first.
well, no. The b will become fixed once we plug it in. A can be whatever. The ax squared is from the when
Okay,
it's one.
let's try this. Two.
Where it should be b.
And then we have 0 equals b plus x. And,
Oh yeah, so it should be.
yeah, b is not.
So it should be bx plus c, and then we can figure out. What
There is a way to let's multiply the differential equation via exponent of integral.
No, I don't solve that like we solved before. You make it equal to 0 first. So it's t prime minus t equal to 0, you solve it.
Okay.
And then you add the x, like we did before.
Maybe I can.
Do you have the final solution?
Hmm?
Do you have the final solution?
Yes,
Because
I do.
It's just an exponent.
because it's
You can define q equals
No,
t.
the solution isn't just exponent.
a substitute. I define z equal y over x. I got something.
Okay. The first step is to understand with what equation you're dealing with, right? I told you that it's first order nonlinear equation, right? Nonlinear because of this. And this well-known equation, it's Bernoulli equation. In canonical form, it look like this. And if we want to solve it, we need to do substitution. Z equals y and
1 minus n.
yeah, like this. Yeah. So in our case,
That's what we did.
n is minus 1. So when we need substitution, z equals minus 7, right? Okay. After substitution, we just have
You should multiply.
basically
This equation.
yeah, this one, right? And we can use integration factor technique.
That's what I'm
Yeah. This is
multiplied by e to power.
just a second. So we have y prime of x plus p of x y of x equals
Q.
yeah p of x like this, right? And when we multiply both sides by mu of x, right? Then we have mu of x y prime of x plus mu of x p of x y of x equal mu q. And then we want that to be u prime. And we got equation for mu. The solution you told us is exponent e to the power
2 over x integral.
Yeah.
2 over x.
Right. And then we know that it's just a formula of derivative of the multiplication. Then we have mu x, y, x, then derivative equals mu q. And then we just integrate both sides and got the answer. In other case, let's rewrite it in this way. So it'd be t prime minus 2 over x t equals 2. Right? And then this is our p of x function. Yeah? And the integrating factor will be e to the minus. So because here's minus, it will be plus. So integral 2 over x dx.
It's just 2.
It will be 2 e to the 2 ln x. And no. Yeah. Okay. Then the answer y is 1 over mu integral q u of x mu of x plus some constant of integration divided by mu. Yeah. So in our case q is just 2, so the answer y of x is 1 over mu, so 1 over x squared, right? Integral 2, then mu of x squared, right? dx plus c divided by x squared. No, it's for z actually, right? For t. Okay. It's not y. It's t. And then we rewrite it to y terms. Okay, then what we have here is 2/3 x plus c over x squared. It's our t. And
t is equal to y squared.
t was equal to
Y squared.
Yeah. So then y of x is square root of this answer, right? Okay. Yeah, I think this is it. In your homework, you have to solve a bunch of differential equations just to just to remember them and apply them in future. And the next tutorial will discuss, I guess, perturbation analysis. Yeah, I hope it will be something new for you.
Yeah, first landed today.
Hmm?
First landed today.
Yeah. In the lecture, right?
Yeah.
Okay. So next tutorial we will solve some problem. If you have any questions, you can ask.
Thank you.
Where do we find the homework? In Lambda?
Yeah. I'll publish it in a couple days. So yeah, and deadlines usually about a week from the publishing date.
Okay. And we submit it online too, right?
Hmm?
We submit it online too, right?
Yeah.
Can you upload the notes before?
Previous?
No.
Ah, notes? Ah, okay. Yeah.
Before the lecture.
Okay, no problem. Yeah. That's for today's lesson. I didn't do any notes because I use.
Oh, you make them.
What else?
No, I use the book of the inventor. I think Asaf told you about this.
No.
So, yeah, sorry, yeah, told you, right?
Yeah, I think in the syllabus.
I don't remember if it's in the syllabus, but it's this book. Advanced mathematical methods for science. You can take a picture, yeah.